next, I've got the distinct pleasure to introduce Professor John James Fick, who is the founder and director of Ultima Capital, based out of Australia. Professor Fick is an adjunct professor with, frankly speaking, I'm not even going to attempt to read out all of the post-nominals, Professor Fick, but having served many years in Ultima Capital since its founding as managing director, following 10 years as a power engineer with the state-owned utility generation in Australia. He's held several managerial positions in large public companies, cable planning for the first broadband submarine cables to Australia, many interesting features on this particular biography. His business experiences are in over 30 countries in advanced technology commercialization, and he serves, as I said, as the director of Ultima Capital, but also several technology and investment companies. Once again, I've had the distinct pleasure of working with John most recently in developing several pilot studies for waste heat recovery, which is something I'm sure we'll hear more about from John during his presentation. Professor Fick, over to you. You'll need to unmute yourself, Professor.
That's it. Well done. And thank you, Rami, and Your Excellency, ladies and gentlemen. I'll just bring up the presentation. Okay. Right. Okay. So it is indeed a pleasure to address you all this evening, my time, from Melbourne, Australia. And the presentation is addressing waste heat recovery opportunities in the desert. Okay, so we'll just move to the next slide. So what's the situation? Well, presently, over 75% of the world's electricity is generated by heat engines, and yet over 70% of that heat is wasted. And more waste heat surrounds us, from gas flares, industrial furnaces, from the exhaust of internal combustion engines to chemical reactions, illustrated here, for example, on the right is the Haber-Bosch ammonia process plant. The opportunities for turning reject heat into electricity with conversion ranges, possibly in the range of 20 to 40%, in every community are boundless, with increasing strategic importance in an increasingly renewable energy-powered world. So why is waste heat recovery important? Well, thermal energy recovery is very complementary and additive to all of the existing energy efficiency technologies. It's very relevant in a clean, renewable generation future. Thermal heat recovery improves the commercial returns of behind-the-meter distributed generation and makes significant reductions to the carbon impulse of high heat commercial and industrial processes. Now, we are advancing energy generation and efficiency technology in a new direction that will prevent, globally, increasing trends of energy lost to heat. And I'll cover a bit more of this in oncoming slides. And of course, there's very significant benefits to the environment, the economy, and to adopting enterprises. Now, our focus is on capturing constrained energy for power generation behind the meter. The core commercial value proposition is based on fuel cost and carbon price avoided. What's the scale of this opportunity? I'm just bringing up here a slide from Lawrence Livermore National Laboratories in the United States, 2019, United States energy flows. This particular diagram on the left shows the sources of energy consumed in the economy of the United States, and on the right, the sinks. Work done through energy services, and the balance is reject heat. One might call it waste heat. Now, the world is increasing the creation of rejected energy every year. We already heard a little bit of that from Pat Scheel in talking about increasing electrification, and within electrified societies, increasing HVAC loads, for example, amongst others. So thermal energy recovery provides a partial solution to convert some of that rejected energy back into energy, completing somewhat of a circular economy for energy. Now, I've had the liberty of attaching to the presentation for your future reference a number of other local economies, the Kingdom of Bahrain. Unfortunately, the most recent such diagram that we could obtain was for the year 2011. And in the case of the United States, the rejected energy proportion was about 68%. Here in Bahrain, it is 63%. So the reject energy opportunity is significant, and we'll focus on which particular applications will be of interest. I've also included some other regional GCC member states, the Kingdom of Saudi Arabia, again, not indifferent to the Bahrain situation from the point of view of natural gas and petroleum. And in the case of all of these countries, we'll see that the source of energy from renewables has escalated significantly and notably since 2011. And perhaps at the next event, we might be able to track and highlight the evolution in revised diagrams. We've also included, for completeness here, the United Arab Emirates, very, very similar to the neighbouring states in terms of energy sourcing. And again, 2011, our apologies for not being able to source anything more recent, but we're working on that. So some basic metrics. So worldwide, there is a massive amount of heat from industrial process that's just dumped into the atmosphere and wasted. So in Europe, in 2015, approximately 300 terawatt hours was rejected. In Australia, the percentage of heat, waste heat rejected is similar, even with all the expected energy efficiency and decarbonisation initiatives afoot. So well over 50% of industrial energy use is to produce temperatures above 350 degrees C. And these are temperatures that facilitate relatively efficient conversion of heat to electricity, which we'll go through. And within emerging and evolving circular economy for energy, there's also considerable potential for energy to be extracted from biomass, biofuels, and waste. So we think about a thermal energy roadmap, and the energy inputs into the energy economy now include reject heat, because we can recycle that, but PV, wind, concentrated solar, bioenergy, and fossil fuels traditionally. Now, in the case of thermal energy, with the thermal energy conversion systems that we're focused on, we'd also focus on thermal energy storage. So that's very important so that we can address episodic, intermittent thermal sources and level those. And in fact, thermal energy storage becomes effectively an energy battery. And that becomes very important in the event of providing some of the other applications. In the case of power generation, non-stop industrial heat, advanced power cycles, fast start gas turbine systems. So the management of reject heat directly supports decarbonisation of many industries. And we call that adding a green jewel into the traditional fossil fueled processes, as well as firming renewable capacities for wind and solar. Getting a bit technical, I won't dwell on this, but there's a sample of thermodynamic cycles for illustrative purposes. We'll talk a little bit about the organic Rankine cycle, also about the Kalina cycle, and we've looked at the trilateral flash cycle that's been used in the case of geothermal applications, another renewable form of heat conversion. Okay, so commercial thermal cycles. Well, commercially available lower temperature thermal engines include organic Rankine cycle, which I've just highlighted, Kalina cycle, typically ammonia based, and the Ericsson cycle. The first two are using working fluids and gases that may also be contributing to global warming. In the case of future developments that might include supercritical CO2 cycles, we can expect to see at higher temperature systems significant increases in efficiencies. Although ORC at lower temperatures, less than 300 degrees C, can operate in a range delivering perhaps up to 20% conversion efficiencies, depending upon many application specific parameters. And a gas-powered cycle, not using a liquid working fluid, but gas, the Ericsson cycle is one such example. And it does have significantly higher potential. It's one that we've been focusing on to address that 50% plus industrial waste heat energy application. There have been many engineering barriers in the case of workability of Ericsson cycle engines. And I've listed some of the details there, but they're now being resolved by one of our enterprises, which we have tagged as the UCP JV. I'll talk a bit about that, but we are bringing to market an advanced Ericsson cycle and achieving almost twice the energy conversion efficiency as the Rankine cycle. With package power blocks of, in small cases, 200 kilowatt electrical is really the bottom end of the system sizing, up to much larger multi-megawatt electrical output systems being designed for industrial and utility-grade power applications. The Barton engine, which we're pleased to be advancing, is a form of Ericsson cycle, and it's a recuperated closed-loop piston cylinder Brayton cycle that generates up to 3 times the electricity from the same heat source as less efficient alternatives. So that's quite a radical step. The thermal engine improves the power density and efficiency to achieve competitive cost per megawatt hour, and also allows the integration very efficiently with a variety of heat sources, including thermal energy storage systems. Now, the key features that we look for in a useful system, I've listed here, but in particular, quick start and quick shutdown is important, as is the higher efficiency at part load with modular systems and reliability that's suitable for utility grade applications with high availability. And when coupled with thermal energy storage, these indicate and lead to non-stop dispatchable power solutions. So the next generation we've talked about is the UCP JV, and we're developing to application stage in Australia the advanced Ericsson cycle. Now, working with a national energy laboratory, CRC Race 2030, in which our organisation, Ultima Capital Partners, is the leading partner. Our partnership is investing over $20 million into further enhancing the performance of the next generation, what we call the Barton cycle. So this leading technology features enhanced power density and efficiency, and it allows integration with heat sources, including large-scale thermal energy batteries. Now, speaking about the thermal energy storage solutions, the systems that are being engineered at the moment are megawatt class, modular, but up to 500 megawatt thermal, enabling very large generation and deep storage capabilities. Now, the applications are varied and wide, and the target end customer market includes designers, builders, operators, and owners of capital-intensive assets that create waste heat. And simply, the higher the waste heat temperature, the better, because thermodynamic efficiency improves with increasing temperature. So our focus is for customers with waste heat sources in 2 ranges. One, 300 degrees Celsius or higher, and that spans a very large number of applications, from incinerators, treatment plants, gas flares, industrial furnaces, cement kilns, gas turbine or diesel engines, glass furnaces. There's a very broad ranging set of opportunities and significant energy conversion opportunities at that. And at the lower temperature range, there's also an equally large number of opportunities spanning boilers, various forms of internal combustion engines, aluminium smelter flue gases, solid thermal collectors, and so on. So there's a very broad range there. What are the design efficiencies? The black line here that we're showing with the black dots is the cycle that we're focused on, is the very high efficiency Barton cycle, and we compare that to other cycles and working fluids, and we've listed some of these different types of examples that we've studied in great detail in recent years. The Barton cycle design efficiency that we're working on at the moment is optimized around 450 degrees Celsius as the operating temperature. And the reason we've done this is to minimize the complications with advanced materials. And this is very important for cost and robustness of the system. I'll come back to ORC because ORC has had to date a larger penetration than the other examples, and there's over 700 ORC installations worldwide, and the bulk of them are on reject heat recovery for internal combustion engine and gas turbines. So you can see that 2/3 of those applications. And then for the rest, so waste to energy is the next largest, and we've had some experiences in a number of these applications over the years. And of course, there is a clear link between energy price. So crude oil price has been correlated with the interest shown in energy recovery systems. But we're going to see further increases in the application here because of the CO2 climate effects, and many organisations now will be factoring in internal carbon price, so more sophisticated multinational organisations and government agencies will be doing that. So applications in the desert. Well, we've started a program with a Sustainable Energy Authority in Bahrain. I'm very pleased to be part of that, and our organisation is working at the moment to identify pilot project sites for thermal energy recovery in industrial and commercial applications. This will set a very solid foundation for local experience and local demonstration of these technologies across the GCC. So what are our interests? Our interests are for developing commercial collaboration within Bahrain for wider business across the GCC, to deploy a number of pilot programs with selected industry as a prelude to scale adoption. Once we've undertaken deployment and verification activities, the local case studies will be documented and will serve as a basis for further informed investment locally. Our organisation in time, will be interested in local joint venture manufacturing in Bahrain for export across the GCC. We're also interested in establishing a technology centre in Bahrain to support regional collaboration with industry, universities, system integration, demonstration, regulation, training, and ongoing development of, if you like, ancillary technologies. And I think fairly importantly, we're interested in expanding an investment platform for the region that can deliver thermal energy recovery projects on a power by the hour basis, if you like, a form of PPA. This is going to become a very rapidly emerging asset class. So decarbonisation is now a strategic necessity for climate change and global business access. Carbon barriers looming. So through thermal energy recovery, we can contribute to economic benefits being delivered to enterprise. And in final form, our team have decades of thermal, power, utility, and energy services expertise. Now, we're based in Australia, but we have global partnerships. We have resources and expertise in modelling and simulation, design and development of systems, their application in selected industries, and importantly, verification. The types of solutions that we spend our time on is not just technical, but also financial, looking at how to package energy services, power by the hour, which I've mentioned, project financing, and joint venture arrangements. And that spans the stack of subsystems from heat exchangers, thermal energy storage, thermal conversion cycles, process integration with the application process, and ultimately turnkey projects. I'd like to thank you very much for your interest in waste heat recovery opportunities and that future in Bahrain and the GCC. Our aim, simply for all of our clients, is to unlock superior value. And through this type of mission, we're certainly in a good place. So thank you very much, ladies and gentlemen.
Professor Fick, thank you for your presentation and all the insights and fantastic graphs. The Sankey diagrams are excellent resources, and as you said, we need to work on updating those, especially for Bahrain from our perspective. Before we delve into any details